Hello and welcome to another video on my channel, math_exe. Today we're going to look at factors and multiples, prime numbers, prime factorization, LCM and GCD, as well as some several examples or problems in the end. So yeah, hope you guys enjoy this video, and thank you. Alright, so first about factors and multiples. We say that m is a factor of n where m and n are integers if and only if n divided by m is an integer, or we can say that m divides n, or n is divisible by m, or there exists some arbitrary integer x such that n is equal to m times x. So these are some ways you can generalize the definition of a factor. So we say 2 is a factor of 12 because 12 divided by 2 is 6, which is an integer. While on contrast, 2 is not a factor of 7 because 7 divided by 2 is 3 halves, which is obviously not an integer. We say that m is a multiple of m if and only if m divided by n is an integer, or m divides m is divisible by n, or there exists some arbitrary integer y. So that's a miswriting there. So there exists a certain integer y such that m is equal to m times y. So let's see. 30 is a multiple of 5, since 30 divided by 5 is an integer. Whereas, let's say 32 is not a factor of 6, for example, since 32 divided by 6 is not an integer, or 32 is not divisible by 6. So let's see. So for example 1, we need to find all factors of 12. Now the way you may do this is that you can check for each integer smaller than 12 and see if 12 divided by that chosen integer is an integer, and therefore that chosen integer is a factor of 12. So after you've done that testing, the factors of 12 will be 1, 2, 3, 4, 6, and 12. And a quick fact, for any arbitrary integer, it must have at least 2 factors, which will be 1 and itself, in this case 12. And for example 2, write down the first 5 multiples of 10. So let's just write multiples of 10. We'll first start off with 10 because 10 is a multiple of itself, and then we can add 10 to get the next multiple 20, add 10 again, add 10 again, and add 10 again, and we stop here because 50 is the 5th multiple of 10. So these are the first 5 multiples of 10. Okay, now about prime numbers and prime factorization. So prime numbers are integers that are only divisible by 1 at itself. So if you think about it, the prime numbers, the list of prime numbers would be 2, 3, 5, 7, 11, 13, 17, 19, and so on. And another fact is that there are infinitely many prime numbers, and there's a proof of that in a video in my channel, so you can look that out. So for the prime factorization of an integer is a way to present that integer by a product of primes, as stated in the fundamental theorem of arithmetic. So for example number 3, we need to express 120 as its prime factorization. So the way I would do that is to construct a factor tree, which is a tree of the list of prime factors of 120, or any integer that you chose. So you can choose any prime number that is less than 120 and check if 120 divided by that prime number is an integer, and then you write it on the right side. So let's say I choose 2, for example. And indeed 2 is a prime factor, so we can write 120 divided by 2, which will be 60. We can continue this. Let's say we choose 2 again. This will leave us with 30 on the right branch, and then you can just do this so on. And once you have left with a prime number on one of the branches, that means you're done. And then you can express 120 as 2 times 2 times 2 times 3 times 5. Or using index form, you get 2 to the power of 3 times 3 times 5. So that's about prime factorization and prime numbers. Finally, about LCM and GCD. So the LCM, or stands for lowest common multiple of 2 or more integers, is the smallest integer that divides or is a multiple of both of the numbers. So for example, the list of common multiples of 2 and 3 is as follows. So you can write the multiples of 2 and the multiples of 3. And then right here, the circled integers are the integers that appear in both lists exactly once. So as you can see, 6 appears on 2 and it also appears on 3. 12 appears on 2 and it also appears on 3. 18 appears on 3 and it appears somewhere right here on 2. So as you can see, if we list down the common multiples of 2 and 3, it will be in a sequence of 6, 12, 8, 24, 30, and so on. And if you want to find the lowest or least common multiple, you can choose 6 because it's the smallest common multiple. So hence, the LCM of 2 and 3 will be 6. In contrast, the greatest common divisor, or GCD, or sometimes known as the highest common factor, or HCF, of 2 or more numbers is the greatest integer that is divisible. The keyword here is divisible by the 2 or more numbers that we have chosen above. So as an example, the GCD of 12 and 18 is 6 because if we list the factors of 12 and the factors of 18, you can see that 6 is the greatest number that appears in both lists. So therefore, the greatest common divisor is 6. However, there is a flaw with this method. If you're dealing with large numbers or pretty large numbers, it is sometimes pretty hard to list down the multiples and factors of that number, and it could be quite confusing and it will waste a lot of time. However, there is a more intuitive way to find the LCM and GCD of any 2 or more numbers, and this is related to prime factorization. And I will demonstrate this in the next example. Here's question 1. For part A, we need to express 90 and 36 as a product of primes. We can use our method of creating a factor tree as like before. So let's say we choose 2, you will get 45. We choose 3, you get 15. You choose 3 again and you 5, and 5 is a prime factor, so we'll stop. So we can rewrite 90 as 2 times 3 squared times 5 using index form. Similarly, we can rewrite 36 as a product of primes as so. So assume that we choose 2, that will leave us with 18. We choose 2 again, we get 9. And then we choose 3, you get 3. And you stop here. So we can rewrite 36 as 2 squared times 3 squared. Alright, for part B, we need to find the LCM and GCD of 90 and 36. So let's just rewrite the prime factorization of each number. And an important key of doing this method is that For every power or every number that has the same base must be on the same column, and this will be very useful later. So let's just write the LCM of these two numbers. So let's just focus a column of a same base. We can take, in this case of the LCM, we can take the number with the largest power right here. So we can assume this is 2 to the first, and of course 2 is greater than 1, so we can choose 2 squared. So let's just write that. Similarly, we can choose either of these because these are exactly the same, and then we can choose 5 because we can act like there is a 5 to the 0, since 5 to the 0 is 1, and 1 is usually neglected in multiplication. And perhaps I'll just write 5 to the first there, so we can choose 5. And you can compute this however you want. For the GCD in this case, instead of choosing the highest power, we'll take the lowest power. So in the case of the column with base 2, we would take 2 because it is the smallest power that exists in that column. So we would take 2. And we would take 3 squared because these are exactly the same, so we can just choose either one of them. Now for here we can choose 5. Well, I'm just joking, we can't, because we can interpret this again. Let me just use the blue marker as 5 to the 0, and then we have 5 to the first. And which power is bigger is obviously 5 to the 0, which is 1. And again, 1 is obviously neglected in multiplication, so we can just write nothing there. So the GCD in this case will be 6. Oh, and if you guys are wondering, the answer for the LCM is 180. So that was the intuitive way to solve for the LCM and GCD. Let's jump into question 2. Right, for question 2, let that bracket A comma B, like this one right here, denote the LCM or lowest common multiple of A and B. And this bracket right here denote the GCD of A and B, where A and B are positive integers. And then we need to evaluate the following right here. So let's just work things inside first. So let me just write the bigger bracket right there. We can solve for the LCM of 16 and 8. And we can just do the same trick like before. So 16, if expressed in as its prime factorization, is 2 to the 4th. 8 will be 2 to the 3rd. Therefore, its LCM will be 2 to the 4th, since we're taking the greatest power in this case. And 2 to the 4th is obviously equal to 16. So it will be 16, 4 plus a big bracket 6, we can find the HCF, or as I should say GCD, of 21 and 14. 21 could be expressed as 3 times 7, 14 could be expressed as 2 times 7. Or let's see, we can express 7 times 2, since the bases, different bases must be in different columns. So therefore the GCD of this will be 7, because we're taking the least power, and we can interpret this as 3 to the 0, which is obviously 1, so we can just choose that, which is oftenly neglected in multiplication. So the GCD of 21 and 14 will be 7. Alright, so we only need to evaluate each of these following. So I'll just skip the rest of the calculation. You can check that the GCD of 16 and 14 will be 4, and the LCM of 6 and 7 will be 42. This will give us an answer of 46. Question 3 is a type of a word problem. Clock A rings every 4 hours, clock B rings every 3 hours, and clock C rings every 6 hours. If the first time that they all ring together is at 9 o'clock, find the second time that they will ring together again. Alright. So this type of problem is asking us to find the LCM of 4, 3, and 6. And again, we can just represent each of these as its prime factorization. 4 is 2 squared, 3 is just 3, let's just put it there. 6 will be 2 times 3. Therefore, its LCM will be, we can just take 2 squared since it is the greatest power, and then we can take 3. So that will leave us with an answer of 12. So since we know that the first time that they all ring together is at 9 o'clock, we can just add 12 to 9 o'clock. So it's just right 9 o'clock plus 12 hours, which will leave us with a time of 21 o'clock or 9 p.m. Alright, for question 4, Kiara baked 30 oatmeal cookies and 48 chocolate chip cookies packaged in plastic containers for her friends at school. She wants to divide the cookies into identical containers so that each container has the same number of each kind of cookie. So you can imagine that all of the containers must contain the exact same number of each type of cookies. If she wants each container to have the greatest number of cookies possible, how many plastic containers does she need? And the keywords here are marked in bold, so let me just label that for you guys. The same number of each kind of cookie and the greatest number of cookies possible. And those really tells us that we must use the GCD. So we must calculate the GCD of 30 and 48. 30, if expressed as its prime factorization, will be 2 times 3 times 5. 48, let me just work that out for you guys. So 48, we can say we choose 2, you get 24. You choose 2, you get 12. You choose 2, you get 6. And then finally, you choose 2 again, you get 3. So using index form, it will be 2 to the 4th times 3. For GCD, you would take the smallest power. So in this case, for this column right here, you would take 2. And then multiplied by 3, you can take either one of these times 1, because we can act like it is 5 to the 0, and we can just take this, which is obviously 1, and it also sometimes will be neglected. So the GCD will be 6. And this is actually how many plastic containers she needs. And just for a bonus question, why not just try to find how many types of cookies that are inside each container? So since we know the number of containers and the number of cookies of each type, we can solve that. Let me just label O for the number of oatmeal cookies in a single container, which will be 30 over 6 or 5. For chocolate chip cookies, there are 48 of them divided by 6, so there will be 8 of them. Alright, so that's question 4. Alright, so here's question 5, which is the last question of this video. 2 neon lights are turned on at the same time. One blinks every 4 seconds and the other blinks every 6 seconds. In 60 seconds, how many times would they blink at the same time? Now the keywords here are that they blink at the same time and they are recurring, or they are in a cycle, since it is labeled as every 4 seconds. So this will tells us that we're supposed to use the LCM, which is the LCM of 4 and 6, more specifically. So 4 can be expressed as 2 squared and 6 can be expressed as 2 times 3. Let's see. So the LCM will take the largest power, which will be 2 squared, times 3. We'll just take that. So that will equal to 12. Right. So it will blink every 12 seconds. And the question is telling us how many times will they blink at the same time in the span of 60 seconds. So that will be 60 over 12, which will be 5. And that concludes this video. So hope you guys enjoyed this. Please subscribe for more videos, and I'll see you guys later. Goodbye.